This video begins the Unit 5 notes on the normal distribution. So recall that in Unit 4 we focused on discrete probability distributions where we considered situations where we could count count outcomes, like the number of times we rolled a certain number on a die, or the number of heads when we would flip a coin so many times. In Unit 5, we will focus on continuous probability distributions. So right now, pause the video and write down 3 examples of a continuous probability distribution. Three continuous probability distributions that I thought of were heights of people, time spent watching TV, and the weight of a certain breed of dog. All right, and remember that all 3 of these are measurements. All right, so continuous probability distributions are often used for measurements because something like heights, for instance, someone could be 60 inches tall, someone could be 61 inches tall, or someone could be right in the middle. They could be 60.5 inches tall. They could be in between the 60 inches and 60.5 inches and be 60.25 inches tall, and so on. We can keep dividing by 2, and we have an infinite number of possible outcomes, so we can't just count them like we could in the discrete probability distributions. Right? So recall that a continuous random variable has an infinite number of possible values that can be represented by an interval on a number line, just like we talked about with the heights. The probability distribution of a continuous random variable is called a continuous probability distribution. So we graphed discrete probability distributions using a histogram way back in Unit 2, but now for continuous distributions, we need to use a probability density function. And for continuous random variables, these functions are curves or graphs. And the most commonly used probability density function is the normal distribution, and all of Unit 5 has to do with this normal distribution. And this formula represents a normal curve. And if you look at it, there's really only 2 things that affect this curve. Those are the mean and the standard deviation. Right? With those 2 values, we can graph the entire normal curve, and we just substitute our x value in to find our probability. Now, with the normal distribution, here is a sketch of one of them. We have its definition and 5 characteristics of the normal distribution here. So first, let's just take a look at this and then pause the video to copy this down. So the normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is called the normal curve. So a lot of times I will just refer to it as a normal curve. And the normal distribution has the following properties. So first, the mean, median, and mode are all equal. Right? We can see that represented on the graph right here. Right? The mean, median, and mode are all equal. Come back to that. The normal curve is bell-shaped and is symmetric about that mean value. And the total area under every normal curve, that's what's shaded in blue there, is always 1. Point number 4, the normal curve approaches but never actually touches the x-axis as it extends farther and farther away from the mean. It goes in each direction Right? It gets closer and closer to the x-axis, but it never actually reaches it. Right? That is called an asymptote. And you may have heard it referred to that in another class. And finally, the fifth characteristic states that between the mean minus 1 standard deviation and the mean plus 1 standard deviation, so we know that that is 1 standard deviation above and below the mean, right? The graph curves downward and the graph curves upwards to the left of 1 standard deviation below the mean and to the right of 1 standard deviation above the mean. Right? So the point at which the curve changes, curving upward and downward, we call those inflection points. So out here, the normal curve is rapidly increasing, and then it slows down to this point where it stops increasing its rate of change, and down here it starts to increase its rate of change again. And this whole idea of inflection points come a lot more into play in calculus. But those inflection points also show us that we have a lot of data values within 1 standard deviation of the mean. So now pause the video to copy this chart down, and you can summarize number 5, talking about the inflection points happening at 1 standard deviation above or below the mean. Or you can copy this chart down, if it's easier to read, from your text on page 236. Right, so let's take a look at 2 examples together. All we want to do with the information we just took down is to determine whether this graph could represent a variable with a normal distribution. So looking at this curve, it does sort of look like a bell almost, but over on the right-hand side, it looks like it's a little lower than the left-hand side, so it's not quite symmetric. Also, the big problem here is both of these kind of, I'll call them tails at either end of the distribution, both of them are below the x-axis. So I would say not normal. And I think we violate point number 2 because it is not symmetric. And we violate point number 4 because the curve passes through the x-axis. In the next example, looking at this, right away I would say this is not a normal distribution. Not normal. Right away we violate rule number 2. It's not symmetric. Right? We would call this more of a skewed right, since we have this kind of tail, or it looks like it's stretched over to the right. So now on the back of your note sheet you have 2 practice problems. Try those 2 practice problems. Pause the video right now. Tell me whether or not they are normal distributions or not, and tell me why. When you're done, start the video back up and check your answers. So in your practice problem number 3, looking at this curve, I would say yes. This is normal, right? Because it satisfies all of our criteria for the normal distribution. And finally, on your last practice problem, I would definitely say no on this one. Not normal. In fact, looking at this, we know we would call this a uniform distribution because it's uniform for all of our x value. And I think we violate all 5 on this one. Number 1, our mean, median, and mode probably not all going to be equal, particularly the mode. With a uniform distribution, we won't have a mode. Number 2, it's definitely not bell-shaped or symmetric. Number 3, the total area under this curve will be greater than 1. If we kind of think of this as a rectangle, but since this is a uniform distribution that continues, since we have the arrows on either end, it's a rectangle where its width goes on forever. So it's a rectangle whose width would be infinity. So its area is definitely greater than 1. We violate number 4 because this distribution does not approach the x-axis. And finally, we violate number 5. We don't have any of those inflection points that occur at the first and second, or sorry, at one standard deviation away from the mean in both the positive and the negative direction. All right, so there was our brief introduction to the normal distribution. Oh, yeah. There was our brief introduction to the normal distribution. In class, we will practice this some more.